Hi kids, now we'll be looking into this moment of inertia thing. I am trying to manage without integration, so it's not compulsory thing. It's like only when you are bored you can look into this video. If you have already started, assuming there will be something inside, there won't be nothing much. Okay, so for a ring, I am trying to find moment of inertia. So this is how you do for integration also, I guess. So when you take moment of inertia about this axis, all the masses are at equal distance, so it is going to be easy way of integration. So it will turn out to be mr square. Avoiding integration in the sense it's like managing without much integration kind of thing, right? So moment of inertia about this axis is going to be mr square. Now by symmetry you can see like if moment of inertia about this axis diameter is I, then about this axis is also I. About any axis is going to be I, about any diameter. So if I take any two mutually perpendicular by using parallel axis theorem, if this is I and this is I, then moment of inertia about this axis will be I plus I, 2I. 2I equals to mr square. 2I equals to mr square, so I equals to mr square by 2. So I think that's how you will be doing for a ring generally. So you will be finding for this one easily by integration, and by using perpendicular axis theorem you will be getting mr square by 2, mr square by 2. So we have done for the ring. So we are going for the rod. Now moment of inertia depends on the mass distribution. So moment of inertia for the rod about the center, I am assuming it as I. This rod's mass is m and length is l. Now this rod you can visualize it as two rods. The same thing I am taking, this one I am putting in green color, this one I am putting in yellow color. Now the thing is, if this moment of inertia about the center is I, then yellow guy's moment of inertia about his center is going to be I by 8. This is what I am going to argue. In order to convince you, I can show you that generally those who know the moment of inertia, they will understand that 1 by 12 factor will be coming generally. But anyway, so if you are taking moment of inertia about the center of the rod, that constant will turn out to be same, some constant into m into length square dimensions, mass into length square dimensions. Moment of inertia dimensions are mass into length square, right? So mass is becoming how much? Mass is becoming half, length is becoming half, so mass into length square will become 1 by 2 into 1 by 2 whole square, which is 1 by 8. So if moment of inertia of this big rod is I about the center, moment of inertia of the small rod is going to be I by 8 by dimensional analysis. Similarly for the green rod also about the center it is going to be I by 8. But we don't want about the center, we need about this axis. So by using parallel axis theorem, if this moment of inertia is I by 8, then moment of inertia about this axis is going to be I by 8 into this rod's mass, which is m by 2 into this length square, L by 4 whole square. So by using parallel axis theorem, moment of inertia for the yellow rod about this axis is going to be this much. By using parallel axis theorem, moment of inertia of the green rod about this axis is going to be I by 8 plus this thing. Now you know you are not changing the mass distribution, so moment of inertia must remain same. So the meaning is this thing plus this thing, that is moment of inertia of the yellow guy about this axis plus green guy about this axis must be same as initial moment of inertia, that is I equals to yellow guy's moment of inertia about that axis plus green guy's moment of inertia about that axis. Now when you solve it, you will be getting ml square by 12, ml square by 12. So the only thing you need to understand here is we didn't use anything like integration, we were just playing around parallel axis theorem here. So we understood this moment of inertia turned out to be ml square by 12. Then by using parallel axis theorem, you can get the moment of inertia about the end of the rod is ml square by 3. So whatever I have done, I will be using it further in some of the derivations. So right now we know what is the moment of inertia of the ring on the rod. So we'll try to find the moment of inertia of the disc. Now disc, what I am doing is I am breaking it into many rods. Now this rod whose length is x and which is at a distance y. So this is my x axis, this is my y axis, and now from this triangle I know x square plus y square equals to r square. Now if I want to find moment of inertia about x axis, then all the masses are at equal distance, so moment of inertia is going to be this mass into y square, that mass into y square for that rod. But if I want to find for the entire disc, I need to integrate, so that's a moment of inertia about x axis. Now if I want to find moment of inertia about y axis, that is a rod, and you can take it as rod of length 2x and this is center, or you can take it like, you can flip this, even if you flip this, moment of inertia will be remaining same. You can take it as a rod of length x but the axis is end, whatever it is. So you can use m l square by 12 where l is 2x, or you can use ml square by 3 where l is x. right? So moment of inertia about y axis is going to be this much, ml square by 3 if I am taking it at the end. Okay, so yes, this is about y-axis, this is about x-axis. Now what I am doing is I am taking moment of inertia about x-axis thing. I am just writing y square is r square minus x square. Y square is r square minus x square. Then I am expanding it. Now dm into x square integral. What is dm into x square integral? That is 3 times of iy. So that is 3 times of iy. Now this is r is constant, so this will turn out to be integral dm into r square. So integral dm is m. Now the good thing is it is symmetrical situation, right? So moment of inertia about this axis and this axis will be same when I calculate for the entire disk. So basically these two are equal. So if I call this as I, then this is minus 3i. When I bring it this side, it will turn out to be 4i, that equals to mr square. So I equals to mr square by 4. So moment of inertia about this axis is mr square by 4, about this axis is mr square by 4. Now by using perpendicular axis theorem about this axis, it will turn out to be mr square by 2. So that's for the disk. Then we are going for solid sphere. Solid sphere I am breaking into many disk. I am taking one such disk whose radius is x and which is at a distance y from the center. Now again I can go with the relation x square plus y square equals to r square. Again I am taking, this is my x axis, this is my y axis. If I want to find moment of inertia about x axis, then I need to find moment of inertia of the disk about the diameter, then use parallel axis theorem. Moment of inertia of the disk about diameter is going to be mr square by 4, that is mx square by 4, and by using parallel axis theorem plus my square. So that is for the moment of inertia of the disk about x axis, moment of inertia about the diameter plus parallel axis theorem. Now if I want to find the total sphere's moment of inertia, I should integrate it. Now similarly, if I want to find moment of inertia about y axis, then it is moment of inertia of the disk about this axis, which is going to be mx square by 2, mx square by 2 about that axis, right? So about the diameter, mx square by 4, about that perpendicular thing, actual axis thing, it is mx square by 2. That's the moment of inertia about y axis for one disk. If you want to find the entire moment of inertia of the sphere, you have to integrate it, right? So once you get this, again we will be going by the same thing. I am taking ix and x square I am writing it as x square itself, y square I am converting it into r square minus x square, y square I am converting it as r square minus x square, right? Then I am expanding it, dm into r square integral turn out to be mr square, integral dm x square. Now this term and this term are similar things, right? So 1 by 4 minus 1, which is 3 by 4 into integral dm x square. Now look at this one carefully, we have got it already here. This is integral dm x square by 2 is iy. So integral dm x square by 2 is iy, so this will turn out to be minus 3 by 2 times of iy. But you know, when you integrate moment of inertia about x axis and y axis has to be same because it is symmetrical thing, right? So these two moment of inertia will be same. I am calling it as I. So when I bring it this side, it will turn out to be 5 by 2 I. So I equals to 2 by 5 mr square. So from here we understood for a solid sphere, moment of inertia about x axis is 2 by 5 mr square. About y axis is also 2 by 5 mr square. So anyway, you know sphere is symmetrical in all three any direction. So about z axis also it will be 2 by 5 mr square. Now hollow sphere. I didn't draw the figure properly, but you can guess if a point mass whose x coordinate is x comma y comma z, that is x, y, z. If you want to find the distance from x axis, then it will turn out to be root of y square plus z square. So moment of inertia will turn out to be dm into root of y square plus z square whole square, which will be dm into y square plus z square. Similarly, moment of inertia about z axis for that particle will turn out to be this thing, y axis. About z axis it will turn out to be this thing. That thing you can manage. Not only hollow sphere, this we can do for like anything, no matter what is the shape. We can say like if I take any one particle whose x coordinate is x, y coordinate is y, z coordinate is z, then moment of inertia of that particle about x axis will be this much, y axis will be this much, z axis will be this much. If you want to find the overall moment of inertia, then you should integrate. But it will turn out to be easy in hollow sphere. So anyway, this part we can do for any object. Now even addition also we can do for any object. So when I add ix plus iy plus iz will turn out to be 2 times of, anyway this is not 3i, this is ix plus iy plus iz for any object. That will be 2 times of integral dm into x square plus y square plus z square. But if it is hollow sphere, then you know moment of inertia about x-axis will be same as y-axis, which will be same as z-axis. So ix plus iy plus iz in this particular question will turn out to be 3i. And every particle is at equal distance, so x square plus y square plus z square will turn out to be r square. So in this particular question, ix plus iy plus iz will turn out to be 3i, and x square plus y square plus z square will turn out to be r square. Other than that, you can write it for any object. For any object, you can write ix plus iy plus iz equals to 2 times of integral dm into x square plus y square plus z square. But in this particular question, it will become 3i and this will become r square. So I equals to 2 by 3 m r square. So moment of inertia about x-axis, y-axis, z-axis, they are equal and is equals to 2 by 3 m r square. Now based on the similar lines, you can see this question. The moment of inertia of a uniform circular ring of mass m and radius are about an axis that passes through the center of the ring and makes an angle 45 degrees with the plane of the ring. So basically they are asking moment of inertia of the ring about this axis, Now I am calling that axis as x-axis, so moment of inertia about this axis is ix. I am taking one more axis like this, which is perpendicular to this, and I am calling it as iy. But you can see by symmetry ix equals to iy, that should be happening. Now I need to take 3 mutually perpendicular axes and in such a way that ix cross iy will be iz, x cross I cross j will be k. So I am taking, if this is the plane, then x-axis is this way, y-axis is this way, z-axis is along the plane. Right? Like this. This is in this direction, this is in this direction, this is in the plane of the ring. Now again, we can use this for any shape, no matter what it is, and we can write this for any shape. But it turned out to be easy in hollow sphere, it will turn out to be easy here also. Now ix and iy both are equal by symmetry, the mass distribution is same. So these two, I and I, if I call it as, then it will turn out to be 2i. And moment of inertia of the ring about diameter we have already calculated in our first question, which is mr square by 2. Now the good thing about this part is, it is a part of a sphere only with this as center. So x square plus y square plus z square for that ring also is r square only. So from here you will be getting I is 3 by 4 mr square. Till here you can do for any object, but it turned out to be easy in the next step for hollow sphere and for this ring thing, right? Consider a uniform thin hemispherical shell of mass m and radius r. What is its moment of inertia about axis passing through the topmost point and the periphery point of its base? See, it is a half shell. You know, for half shell, center of mass will be at a distance r by 2. So if this is r by 2, this will be r by 2. So if you know moment of inertia about this axis, then if you want to find moment of inertia about this axis, it is like IC plus m into perpendicular distance square. But if you notice this one, now moment of inertia about this axis and this axis is going to be same, because this perpendicular distance and this perpendicular distance is going to be same. That you can manage by yourself. Now our aim is to find moment of inertia about this axis, but what we will do, we will convert our aim as finding moment of inertia about this axis. We understood moment of inertia about this yellow axis and this yellow axis will be same by parallel axis theorem, and moment of inertia finding moment of inertia about this axis is going to be easy. That you can manage. That is 2 by 3 mr square. If you want, you can just bring one more hemispherical shell, then it will become full shell. Full shell's moment of inertia will be 2 by 3 times of, then mass is going to be 2m. 2 by 3 times of 2m into r square, that equals to 2 times of I. If you assume this is I, if you bring one more hemispherical shell, then the total moment of inertia will become I plus I, 2i. 2i equals to 2 by 3 into 2m into r square. 2 and 2 will be getting cancelled. You will be getting I equals to 2 by 3 mr square. So basically you need to find moment of inertia about this axis, but you are converting that aim into finding moment of inertia about this axis, which is easy to calculate. Okay, so basically you need to find what is the moment of inertia of triangular lamina, equilateral triangular lamina about this axis. Again we will be going with the similar method. So this big equilateral triangle, I can visualize it like 4 small equilateral triangles. So I want to find moment of inertia about this axis. I am calling it as I. If moment of inertia about this axis is I am going to argue moment of inertia of this green triangle about this axis is going to be I by 16, because mass is becoming 1/4, length is becoming half, mass is becoming 1/4, length is becoming half, so moment of inertia will become 1/16. So moment of inertia of the green triangle about this axis is going to be 1/16, white triangle about this axis is going to be 1/16, yellow triangle about this axis is going to be 1/16. About this axis is going to be 1/16, but I need to find moment of inertia about this axis. That will be I/16 plus parallel axis theorem. This mass is m/4 and this distance is l/4. Now moment of inertia of this triangle about this axis is going to be I/16, but I need to find about this axis, which will turn out to be I/16 plus m/4 into l/4 whole square. So if this moment of inertia is I about this axis, then green color's moment of inertia about this axis will be I/16, white guy's moment of inertia about this axis will be I/16, yellow guy's moment of inertia about this axis will be I/16, but about this axis it will be I/16 plus m/4 into l/4 whole square. Of brown color thing about this axis is going to be I/16, about this axis is going to be I/16 plus m/4 into l/4 whole square. But you know, figure is same, so moment of inertia must be same in both the cases. So I is equals to moment of inertia of the white guy plus the green guy plus the yellow guy plus the brown guy. So when you solve for it, you will be getting ml square by 24. So moment of inertia of equilateral triangular lamina about this axis is ml square by 24. Now similarly, there is other question here. A uniform equilateral triangular lamina of side length L and mass m, its moment of inertia about the axis passing through the centroid and perpendicular to the plane. So about this axis you need to find. Again we will be going by the same thing. I am assuming moment of inertia about this axis is I. If moment of inertia about this axis is I for this big triangle, for this small triangle it will be I/16, because mass is becoming 1/4 and length is becoming half. By dimension analysis I can say moment of inertia of the green color guy about this axis is I/16, white color guy about this axis will be I/16, yellow color guy about this axis will be I/16, brown color guy about this axis will be I/16. Now you see this point and this point are same. Centroid of the bigger white triangle will be same as smaller white triangle. Now if I want to find moment of inertia of green guy about this axis, then I need to use parallel axis theorem. I/16 plus m/4 into this distance square. The distance will be l/2√3. You can calculate it. Now similarly for this guy also it is the same, for this guy also it is the same. So now moment of inertia of this entire triangle is same as moment of inertia of these four triangles about that axis. So I equals to I/16 for white guy, for yellow guy I/16 plus parallel axis theorem, for green guy I/16 plus parallel axis theorem, for a brown guy I/16 plus parallel axis theorem. When you solve it, you will be getting ml square by 12. So moment of inertia of equilateral triangular lamina about this axis is ml square by 12. Now what we understood is, if there is a equilateral triangular lamina about this axis, it turned out to be ml square by 24. About this axis it turned out to be ml square by 12. Yeah, so there is some kind of theorem, I don't know like from where it came. So but how it works is this thing. If you replace the entire mass, I mean if you want to find the moment of inertia of this, not only equilateral, I will show like it is valid for any triangle, but let us go for equilateral. So if I take this equilateral triangle and I just put that imaginary triangular figure and the total mass is m, so I am breaking it into 3 masses, m/3, 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 and I am going to put one point at this midpoint of the line and midpoint of this line 1 m/3, midpoint of this line 1 m/3. Then if you calculate moment of inertia about this axis, then it will turn out to be m/3 into this distance square plus m/3 into this distance square, and this moment of inertia will be 0. So m/3 into this distance square plus m/3 into this distance square plus 0. When you calculate, it will turn out to be ml square by 24. Similarly, if you want to calculate moment of inertia about this axis, then it is m/3 into this distance square plus m/3 into this distance square plus m/3 into this distance square. When you calculate, it will turn out to be ml square by 12. So basically, whenever there is triangle, if you replace with m/3 at the midpoints of the sides, then you are getting the same moment of inertia. So if we extend this argument, you will be expecting moment of inertia of triangular lamina about the base. This again is going to be little hard, maybe probably we will go with integration, but if we go with the same argument and see like how much it can turn out to be, so if it is valid, if the argument is valid, it will turn out to be something like, you can replace this one with m/3, 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 then moment of inertia about this axis for this guy is going to be 0, for this guy it is going to be m/3 into this distance square, for this guy m/3 into this distance square. When you do the calculation, it will turn out to be ml square by 8. Anyway, I don't have a first of all, I don't have written PDF like what is the moment of inertia of equilateral triangular lamina, but I'll show you for any generalized triangle kind of this. You can read the question. Two triangular plates ABC and ABD of same thickness and height and mass are shown. The moment of inertia of these plates about the axis PQ. So these two plates will be having the same moment of inertia. That's what the answer says. Anyway, that will come from here. Generally, if you do the integration for any triangular plate, it depends on only the height and the mass. 1 by 6 mh square. So area will be remaining same, so mass will be remaining same, height is remaining same. Base is remaining same, right? Base is remaining same, height is remaining same, so area will be remaining same, so mass will be remaining same. Mass is remaining same, height is remaining same, moment of inertia will be remaining same. So basically, this is the integration way of proving mh square by 6. Now, once you know this thing, then you can cross check whether this is correct or not. H is root 3 by 2L, right? So you can substitute H is root 3 by 2L and you will understand this is going to be correct only. Anyway, so we have understood like something was working, so we'll just check whether it will be working here or not. So for this question, any triangular lamina, moment of inertia about the base is mh square by 6, so I'll be going by the same thing. This is triangular lamina, this is not equilateral. I have just borrowed the figure of equilateral triangle, but you can say I won't be using equilateral thing anywhere here. Yes, so I can replace it with 3 points and I need to find moment of inertia about this axis. Moment of inertia of this guy is 0. Moment of inertia of this guy, no matter whether it is equilateral or not, when you take a midpoint, this height will be h by 2, this height will be h by 2. So for this guy it is 0, for this guy m by 3 into h by 2 whole square, for this guy m by 3 into h by 2 whole square, which will turn out to be 1 by 6 mh square, which was the same result we got by integration. If someone can't remember the result, you can just kind of remember this method, which can give you the result quickly. I am yet to figure out like from where this method came in the first place. Right, so about the base it is mh square by 6. So once you understand this, the previous question is going to be pretty easy. Yes, that's all, and these things I think everyone will be knowing. Moment of inertia of square lamina about this axis, if you want to find, what you will do is you will compress this square lamina, because you know even if you put this point here or here or here or here, moment of inertia about this axis is not going to change because you are not changing the perpendicular distance. Once you understand that, you will compress the square. Once you compress the square, you will get a rod of length of mass m and length a. So moment of inertia will be ml square by 12, that is ma square by 12. Similarly, if you want to find moment of inertia about this axis, you will compress it like this, then you will get ma square by 12. Then by using perpendicular axis theorem, you will get this moment of inertia is ma square by 6. Now once you understand that, if someone asks you what is the moment of inertia about the diagonal, you will take one more diagonal and you will say those two are perpendicular and mass distribution is same. So if this moment of inertia is I, this moment of inertia also will be I, but I plus I you already know it is ma square by 6. So 2I is ma square by 6, so I is ma square by 12. Now once you understand this is also ma square by 12, then you can easily prove moment of inertia about any axis which is in the plane of square and passing through the center. Moment of inertia about that axis is going to be ma square by 12. Now how we are going to prove it is, we will be taking one perpendicular axis for that, and we can see like mass distribution is going to be same for this axis as well as this axis. So if this moment of inertia is I, this moment of inertia also will be I, but those two are perpendicular, so I plus I is 2I. By using perpendicular axis theorem, 2I is ma square by 6, so I will be ma square by 12. So basically about any axis which is in the plane of square lamina passing through the center of mass, moment of inertia is going to be ma square by 12. Now similar thing for hollow cone. For a hollow cone, you will be going with integration. You will be taking some ring, you will be finding the moment of inertia of the ring and you will be integrating. But when you integrate, the result looks like something like this, which is like moment of inertia of element of a disc. So basically when you integrate, you are getting a moment of inertia of the disc, which makes sense because after integration it makes sense to me. For some people it makes sense in the beginning itself. Basically when you compress a cone from the top, this blue thing will exactly fall at the same distance. So a perpendicular distance from the axis is not going to change. When you compress the cone, it is going to become a disc, and if you mark different layers in different colors, let me say this is blue, the next one is red, though when you compress it, then blue will be there, red will be there, the radius is going to remain same kind of thing. Then you can visualize when you compress a hollow cone, it is going to become a disc. So hollow cone's moment of inertia is mr square by 2, disk moment of inertia is mr square by 2, right? So Hall accounts moment of inertia and disk moment of inertia is going to be same. That must make sense now, right?